Curves are a fundamental concept that permeates almost every aspect of our world, from the natural formations that shape the landscapes around us to the engineered designs that define our built environment. They are essential in the arts, influencing everything from painting and sculpture to music and dance, and they also play a critical role in science, where they help describe everything from the trajectory of a particle to the arc of a planet's orbit. Curves, in their various forms, are ubiquitous, influencing the way we interact with and understand the world. A reverse curve is a special type of curve that holds a unique place in this broad spectrum. Unlike a standard curve, which typically follows a smooth, continuous path in a single direction, a reverse curve changes direction, bending in the opposite way. Imagine a road that bends left, only to bend right shortly after, or a river that makes a sharp S shape as it winds through the landscape. These are simple examples of reverse curves in action. To truly understand reverse curves, one must first grasp the essential properties that define them. A reverse curve is often characterized by its distinct change in direction, creating a path that appears to fold back on itself. This change can occur gradually or sharply, depending on the context in which the reverse curve is found. In mathematical terms, a reverse curve can be described using geometry and calculus, where the curvature of the path changes sign. If a curve initially bends to the left, a negative curvature, and then transitions to bend to the right, a positive curvature, it forms a reverse curve. The point at which this transition occurs is often referred to as the point of inflection, where the curve's concavity changes direction. Reverse curves are not just mathematical abstractions, they have real-world implications and applications. They are used extensively in various fields, including engineering, architecture, transportation, and even art. The unique shape allows them to fulfill specific functions that a regular curve cannot, particularly in situations where space, safety, or aesthetics are key considerations. The use of reverse curves can be traced back to ancient times when architects and engineers began to recognize the practical and aesthetic benefits of this shape. In the construction of Roman aqueducts, for example, reverse curves were employed to navigate difficult terrains while maintaining a stable water flow. The ancient Greeks, too, utilized reverse curves in their architecture, as seen in the subtle curvature of the Parthenon's columns, designed to counteract optical illusions and create a more pleasing appearance. As civilizations advanced, the application of reverse curves expanded. In the 19th and 20th centuries, with the advent of modern engineering and transportation, reverse curves became an integral part of road and railway design. Engineers realized that incorporating reverse curves into the layout of roads and tracks could help manage the forces exerted on vehicles, enhancing safety and comfort for travelers. This practical application of reverse curves has only grown in importance with the increasing complexity of modern infrastructure. Beyond their functional applications, reverse curves have also played a significant role in the world of art and design. The human eye is naturally drawn to curves, finding them more pleasing and dynamic than straight lines or sharp angles. Reverse curves, in particular, create a sense of movement and flow, leading the viewer's eye along a path that is both intriguing and harmonious. In art, reverse curves can be seen in everything from the elegant swirls of Baroque architecture to the fluid forms of Art Nouveau. These curves introduce a sense of rhythm and balance, guiding the observer through the composition. In sculpture, reverse curves add dynamism and tension, as seen in the twisting forms of works by artists like Auguste Rodin and Henry Moore. The interplay of opposing curves creates a visual tension that makes the artwork feel alive and in motion. Similarly, in graphic design and typography, reverse curves are often used to create visually engaging compositions. The letter S, for example, is essentially a reverse curve, and its shape has been employed creatively in logos, posters, and other designs to evoke a sense of fluidity and elegance. Nature, too, is full of reverse curves, demonstrating their fundamental role in the natural world. One of the most common examples is the meandering path of a river. As a river flows across a landscape, it often forms a series of reverse curves, creating the familiar S shapes that characterize many river valleys. These curves are not just beautiful, they also play a crucial role in the river's ability to transport sediment and maintain its course. The concept of reverse curves can also be found in the growth patterns of plants and animals. For instance, the tendrils of climbing plants often exhibit reverse curves as they wind around supports, maximizing their grip and stability. In the animal kingdom, the graceful curves of a fish's body or the undulating movement of a snake can also be seen as examples of reverse curves in action, allowing these creatures to move efficiently through their environments. What makes reverse curves so fascinating is their ability to combine functionality with beauty. They are more than just a tool for engineers or a motif for artists. They represent a deeper connection between the physical world and the way we perceive and interact with it. Reverse curves challenge our expectations, drawing our attention and inviting us to explore the paths they create, whether in a physical space or a conceptual one. In the realm of physics and engineering, reverse curves are far more than mere aesthetic elements. They are vital components that enhance functionality, safety, and efficiency in various applications. From road design to structural engineering, reverse curves play a critical role in shaping the built environment and ensuring that it functions optimally. This chapter will delve into the principles behind reverse curves, exploring how they are utilized in different engineering fields and why they are essential to the physical world we interact with daily. At the core of the reverse curve's utility in engineering is the concept of curvature, which describes how sharply a curve deviates from being straight. In physics, curvature is directly related to the forces experienced by objects moving along the curve. When a vehicle, for example, navigates a curved path, it experiences a centripetal force that pulls it towards the center of the curve. This force is necessary to keep the vehicle on its path, but it can also create challenges, particularly at high speeds. A reverse curve, which changes direction, introduces an additional layer of complexity. As a vehicle moves through a reverse curve, the direction of the centripetal force changes, which can affect the vehicle's stability and the comfort of its passengers. Engineers must carefully consider these forces when designing roads, railways, and other infrastructure that incorporates reverse curves. By understanding the physics of reverse curves, they can optimize the design to minimize risks and maximize performance. One of the most common and critical applications of reverse curves is in the design of roads and railways. These infrastructure elements are essential to modern transportation, and the design directly impacts safety, efficiency, and the overall user experience. In road design, reverse curves are often used to navigate challenging terrains, such as mountainous regions or areas with limited space. A well-designed reverse curve allows a road to change direction smoothly, reducing the need for abrupt turns that could be dangerous for drivers. However, reverse curves must be carefully engineered to ensure that vehicles can navigate them safely, especially at higher speeds. When designing a reverse curve in a road, engineers consider several factors. Radius of curvature. The radius of the curve affects how sharply the road bends. A smaller radius results in a tighter curve, which can be more challenging for drivers to navigate. Engineers must balance the need for space with the need for safety, often opting for larger radii where possible to reduce the risk of accidents. Superelevation. Superelevation, or banking, is the practice of tilting the road surface to counteract the lateral forces experienced by vehicles as they navigate a curve. In a reverse curve, the direction of this tilt must change to match the changing direction of the curve. Proper superelevation is crucial in ensuring that vehicles maintain traction and stability throughout the curve. Transition curves. To further enhance safety, engineers often use transition curves, or spiral curves, at the beginning and end of a reverse curve. These transition curves gradually introduce the curvature, allowing vehicles to adjust their speed and direction smoothly. This reduces the risk of sudden movements that could cause loss of control. Reverse curves are also a common feature in railway design, where they are used to navigate complex terrain or urban environments. The principles are similar to those in road design, but there are additional considerations due to the nature of rail vehicles. Railway vehicles, particularly trains, have longer wheelbases and are less flexible than road vehicles. This makes it more challenging for them to navigate sharp curves, including reverse curves. Engineers must ensure that the curves are designed with a large enough radius to accommodate the train's length and that the tracks are laid with precision to avoid derailment. In addition to the radius of curvature and superelevation, railway engineers must also consider the following. Track alignment. The alignment of the tracks through a reverse curve is critical. Any misalignment can lead to uneven wear on the tracks and wheels, increasing the risk of derailment or other accidents. Precision in track laying is therefore essential. Cant deficiency. Cant deficiency occurs when a train travels through a curve at a speed higher than what the superelevation is designed to accommodate. This can lead to discomfort for passengers and increased wear on the tracks. Engineers must carefully balance speed limits with the design of reverse curves to minimize cant deficiency. Reverse curves are not limited to transportation, they also play a significant role in structural engineering and architecture. In these fields, reverse curves are often used to create visually striking designs that also serve practical purposes. In bridge design, reverse curves can be used to create elegant, flowing structures that blend seamlessly with their surroundings. For example, a bridge spanning a river may incorporate a reverse curve to follow the natural contours of the landscape. This not only enhances the aesthetic appeal of the bridge but also minimizes the environmental impact by reducing the amount of earth that needs to be moved during construction. Reverse curves in bridges must be carefully engineered to handle the loads they will bear. The changing direction of the curve introduces varying stresses on the structure, which must be accounted for in the design. Engineers use advanced modeling techniques to analyze these stresses and ensure that the bridge can safely support both static and dynamic loads. In architecture, reverse curves are often used to create dynamic and visually interesting spaces. Buildings with curved facades or interiors can evoke a sense of movement and fluidity, making them stand out from more traditional, rectilinear designs. Reverse curves can be found in everything from the sweeping lines of a modern skyscraper to the graceful arches of a historic cathedral. Beyond aesthetics, reverse curves in architecture can also have practical benefits. For example, curved walls can help distribute structural loads more evenly, reducing the need for additional support. They can also improve acoustics by minimizing echoes and creating a more pleasant sound environment. Safety is a paramount concern in any engineering project, and reverse curves present unique challenges that must be addressed. Whether in road design, railway engineering, or structural projects, engineers must consider how the changing direction of a reverse curve affects the forces experienced by the structure or vehicle and how these forces can be managed to ensure safety. One of the key safety considerations is the risk of rollover or loss of control. In road design, vehicles that enter a reverse curve at too high a speed may be unable to navigate the change in direction, leading to skidding or rollover accidents. To mitigate this risk, engineers design reverse curves with appropriate speed limits and signage, ensuring that drivers have enough warning to adjust their speed before entering the curve. In railway design, the risk of derailment is a significant concern. Trains traveling through a reverse curve must do so at a speed that allows the wheels to maintain contact with the tracks at all times. Engineers carefully calculate the appropriate speed limits for each curve, taking into account the train's weight, speed, and the curve's radius. In structural engineering, safety considerations include ensuring that the structure can withstand the varying stresses introduced by the reverse curve. This requires careful analysis of the materials used, the load distribution, and the environmental conditions the structure will face. Nature has always been a master architect, sculpting landscapes and organisms with intricate designs that serve specific purposes. Among these designs, reverse curves emerge as a recurring theme, playing vital roles in the survival and functionality of living organisms and natural systems. In this chapter, we will explore the presence of reverse curves in the natural world, from the sinuous paths of rivers to the spiraling growth patterns of plants and animals. We will delve into the reasons why these curves occur and how they contribute to the stability, efficiency, and beauty of natural forms. One of the most recognizable examples of reverse curves in nature is found in the meandering paths of rivers. As rivers flow across landscapes, they rarely follow a straight course. Instead, they often curve back and forth, creating a series of S-shaped bends known as meanders. These meanders are a classic example of reverse curves in action, and they play a crucial role in the river's ecological and geological processes. Meanders form as a result of the interaction between the river's flow and the landscape it traverses. When a river flows through relatively flat terrain, variations in the speed and direction of the water create areas of erosion and deposition along the riverbanks. Over time, these processes cause the river to curve, as the faster-moving water on the outside of a bend erodes the bank, while slower-moving water on the inside of the bend deposits sediment. As the river continues to flow, these bends become more pronounced, eventually leading to the formation of reverse curves. The river may shift course over time, abandoning older bends and creating new ones. This dynamic process is a key driver of landscape evolution, contributing to the formation of floodplains, oxbow lakes, and other features. The reverse curves of meandering rivers create a variety of habitats that support diverse ecosystems. The bends in the river create zones of slow-moving water where sediment can settle, providing fertile grounds for plant growth. These areas, known as point bars, are often rich in nutrients and serve as breeding grounds for fish and other aquatic species. On the outside of the bends, where the river erodes the bank, steep cliffs or bluffs may form. These areas can become important nesting sites for birds or provide shelter for other wildlife. The constant reshaping of the river's course also promotes biodiversity by creating a mosaic of habitats that support different species at various stages of succession. Plants, too, often exhibit reverse curves in their growth patterns, utilizing these shapes to enhance their stability, maximize exposure to light, or secure their position in the environment. From the spiraling tendrils of climbing plants to the coiling stems of certain flowers, reverse curves are a common feature in the plant kingdom. Climbing plants, such as vines, use reverse curves in the form of spiraling tendrils to grasp onto supports as they grow. These tendrils are specialized structures that can sense nearby objects and wrap around them, securing the plant's position and allowing it to reach greater heights. The reverse curve of a tendril, which changes direction as it coils, provides a strong and flexible grip, enabling the plant to withstand environmental stresses such as wind or the weight of its own growth. The formation of these spirals is driven by differential growth rates on different sides of the tendril. As one side of the tendril grows faster than the other, it causes the tendril to bend and eventually form a coil. This growth pattern is an excellent example of how reverse curves can emerge from simple biological processes to serve a critical function in the plant's survival. In some plants, the stems or flowers exhibit helical growth patterns, creating reverse curves as they spiral upwards. This growth form, known as circumnutation, is often seen in plants like morning glories or certain types of ferns. The reverse curves in these spirals allow the plant to maximize its exposure to sunlight by orienting its leaves or flowers in multiple directions. This helical growth pattern also helps the plant distribute mechanical stress more evenly along its stem, reducing the likelihood of damage from environmental forces such as wind or heavy rainfall. The reverse curves in the spiral allow the plant to be both flexible and strong, adapting to changing conditions while maintaining structural integrity. In the animal kingdom, reverse curves are often found in the anatomy and movement patterns of various species. These curves can provide functional advantages in terms of locomotion, stability, and flexibility, allowing animals to navigate their environments more effectively. One of the most striking examples of reverse curves in animal movement can be observed in the undulating locomotion of snakes. As a snake moves, its body forms a series of reverse curves, creating S-shaped waves that propel it forward. This type of movement, known as lateral undulation, is highly efficient and allows snakes to traverse a wide range of terrains, from sand to water to dense undergrowth. The reverse curves in a snake's movement are generated by the coordinated contraction and relaxation of muscles along its body. By alternating the direction of these contractions, the snake creates a wave-like motion that pushes against the ground, allowing it to move smoothly and quickly. This movement pattern is not only efficient but also enables the snake to maneuver through tight spaces and over obstacles with ease. In many species of mammals, reverse curves can be seen in the shape of their horns or antlers. Animals such as rams, goats, and certain species of deer possess curved horns or antlers that often form spirals or arcs. These reverse curves serve both practical and symbolic functions. From a practical perspective, the curved shape of horns or antlers helps to distribute the force of impacts during fights or clashes with other animals. When two animals collide head-on, the reverse curve in their horns can absorb and redirect some of the energy, reducing the risk of injury. Additionally, the spiral or curved shape allows for stronger and more resilient structures, capable of withstanding the pressures of combat or environmental challenges. Symbolically, the reverse curves of horns or antlers are often associated with power, dominance, and fertility in various cultures. These shapes have been depicted in art and mythology throughout history, representing the strength and vitality of the animals that possess them. In the aquatic world, reverse curves can also be found in the anatomy and movement of fish and other marine life. The streamlined bodies of many fish species feature reverse curves that help reduce drag as they swim through water. The S-shaped movements of eels, for example, are a classic example of reverse curves in action, allowing these creatures to navigate through narrow crevices and around obstacles with agility and precision. The tails of many fish, which often feature a reverse curve, are also critical to their locomotion. As the tail moves from side to side, the reverse curve allows the fish to generate thrust and steer efficiently, contributing to its speed and maneuverability in the water. Beyond living organisms, reverse curves are also prevalent in geological formations and landscapes, where they influence the distribution of natural resources, the formation of landforms, and the overall stability of the environment. In mountainous regions, reverse curves can be seen in the sinuous paths of valleys carved by rivers or glaciers. As these natural forces erode the landscape, they often follow paths of least resistance, which may change direction as they encounter different types of rock or geological structures. The resulting valleys often exhibit reverse curves, winding through the mountains in patterns that reflect the underlying geology. These curved valleys are not only visually striking but also play a crucial role in the hydrology and ecology of the region. The reverse curves help distribute water flow more evenly across the landscape, reducing the risk of erosion and providing diverse habitats for plants and animals. Along coastlines, reverse curves are a common feature of cliffs and coastal landforms. As waves erode the base of a cliff, the rock above may collapse, creating a curved indentation in the landscape. Over time, this process can lead to the formation of sea arches, stacks, and other coastal features that exhibit reverse curves. These curved landforms are constantly reshaped by the forces of erosion and weathering, creating dynamic environments that are home to a variety of marine and terrestrial species. The reverse curves in these landforms also contribute to the overall stability of the coastline, as they help dissipate the energy of incoming waves and reduce the impact of erosion. One of the most remarkable aspects of reverse curves in nature is the way they seamlessly blend functionality with beauty. Whether in the flowing path of a river, the spiraling growth of a plant, or the undulating movement of an animal, reverse curves are not only effective solutions to specific challenges but also contribute to the aesthetic appeal of the natural world. This interplay between functionality and beauty is a testament to the elegance of natural design. Reverse curves, with their dynamic shapes and fluid movements, capture our attention and evoke a sense of wonder. They remind us that nature, in its endless creativity, has a way of finding solutions that are both practical and pleasing to the eye. Reverse curves have long held a significant place in the realms of art, architecture, and design. These shapes, with their fluidity and elegance, have been utilized by artists, architects, and designers throughout history to create works that resonate with both aesthetic appeal and functional brilliance. In this chapter, we will explore how reverse curves have been employed across various mediums, from classical sculptures to modern architecture, and how they continue to inspire contemporary design. In classical art, reverse curves have often been associated with grace, movement, and beauty. The ancient Greeks, for example, frequently used the concept of the contrapposto pose in their sculptures, where the human figure is depicted with a naturalistic shift of weight that creates a subtle reverse curve in the body. This pose, which places the body in a gentle S-shaped curve, not only adds a sense of dynamism and fluidity to the sculpture but also reflects the balance and harmony that was central to Greek aesthetics. The use of reverse curves in classical art can also be seen in the flowing lines of drapery in sculptures and paintings. Artists would carefully carve or paint the folds of garments in sinuous, reverse curves to enhance the sense of movement and to draw the viewer's eye across the composition. These curves help convey the softness and fluidity of fabric, adding to the lifelike quality of the artwork. Architecture has also made extensive use of reverse curves to achieve both structural and aesthetic goals. In Gothic cathedrals, for instance, the pointed arches and ribbed vaults often incorporate reverse curves, creating soaring, elegant spaces that direct the eye upwards. These curves are not only visually striking but also serve a functional purpose, distributing the weight of the structure and allowing for the construction of tall, open interiors filled with light. The Baroque period took the use of reverse curves in architecture to new heights, with its emphasis on dramatic, flowing forms. Baroque architects employed reverse curves in the design of facades, interiors, and even entire building layouts, creating spaces that felt dynamic and alive. The undulating forms of Baroque churches, with their curved walls and ceilings, create a sense of movement and energy, drawing visitors into a spiritual and emotional experience. In modern architecture, reverse curves continue to inspire innovative designs. Architects like Zaha Hadid, known for her futuristic and fluid forms, often incorporate reverse curves into her buildings, creating structures that seem to defy gravity and traditional notions of space. These curves allow for new ways of thinking about architecture, where form and function are seamlessly integrated. In the world of design, reverse curves are often used to create products that are both ergonomic and aesthetically pleasing. In industrial design, for example, the curves of a chair or a car may be designed to fit the contours of the human body, providing comfort while also creating a visually appealing form. The reverse curve, with its natural, flowing shape, helps designers create objects that feel intuitive and harmonious. Fashion design has also embraced the reverse curve, particularly in the creation of garments that enhance the natural lines of the body. The hourglass figure, often emphasized in women's fashion, is essentially a reverse curve, with the waist curving inward while the hips and bust curve outward. This shape is celebrated for its femininity and elegance, and designers have used it to create clothing that flatters and accentuates the wearer's form. In addition to clothing, accessories such as jewelry often feature reverse curves. The curves of a necklace, for instance, are designed to drape elegantly around the neck, creating a graceful line that complements the wearer's natural shape. The use of reverse curves in jewelry design adds a sense of fluidity and movement, making the pieces feel alive and dynamic. Beyond their practical applications, reverse curves have also taken on symbolic meanings in various cultures. In many traditions, curves are associated with femininity, the cycle of life, and the natural world. The reverse curve, with its inherent sense of movement and change, can symbolize growth, transformation, and the passage of time. In Eastern art and philosophy, the concept of the yin and yang embodies the idea of balance through opposites, often depicted as a reverse curve where the two forces flow into each other. This symbol, with its flowing curves, represents the interconnectedness of all things and the harmony that arises from balance. In Western culture, reverse curves have often been associated with beauty and sensuality. The curve of a body, a flower, or a river is seen as a representation of nature's perfection, a shape that is both pleasing to the eye and reflective of deeper, more profound truths. As we look to the future, the concept of reverse curves continues to inspire innovation across various fields. In architecture and urban planning, reverse curves are being explored to create more resilient and sustainable structures that can better withstand natural disasters, like earthquakes and floods. These designs, which incorporate fluid, curved forms, distribute stress more evenly, enhancing the durability and flexibility of buildings. In transportation, reverse curves are used to design safer and more efficient roadways and railways. The gentle curves help reduce accidents by allowing smoother transitions between directions, improving visibility and control for drivers and engineers. The automotive and aerospace industries are also utilizing reverse curves in vehicle design to enhance aerodynamics, reducing drag and increasing fuel efficiency. In technology and robotics, reverse curves are being studied to create more natural and adaptive movements in machines. Biomimicry, where engineers draw inspiration from the curves found in nature, is leading to advancements in robotics, prosthetics, and wearable devices that move more fluidly and intuitively. Ultimately, the study and application of reverse curves demonstrate how this simple yet profound concept can lead to significant advancements in both our understanding of the natural world and our ability to innovate in ways that harmonize with it. As designers and engineers continue to explore the potential of reverse curves, we may see new solutions to complex challenges that are not only functional but also embody the elegance and beauty that these curves have long represented.